So far in the class, we've learned how to talk about points in space and also how to describe points using vectors. We just talked about this idea of vector function, that I have a function that every time I plug in a value of t, I get out a vector. And that vector is pointing from the origin to a point on a curve, right? The functions f, g, and h are scalar functions that give me parametric equations for the curve. We're finally at a place where we can start talking about calculus concepts. The calculus of vector functions, to be specific. So the first concept we need to come across is that of the limit. Let r of t be the vector function f of ti plus g of tj plus h of tk. Then we say r of t has the limit L, where L has components L1, L2, and L3, as t approaches t naught, and we write the limit as t approaches t naught of r of t is the vector L if the limit as t approaches t naught of the I component is the I component of L, the limit as t approaches t naught of the j component is the j component of L. And then similarly for the k component, the limit as t approaches t naught of h has to be L3. What this definition says is my vector function has a limit of L with components L1, L2, and L3 if my scalar component functions have the limits L1, L2, and L3 respectively. What's even better than that is this definition gives us a way of evaluating the limits of vector functions. We simply evaluate the limit of each component function one at a time. So I have an example here. R of t is cosine ti plus sine tj plus sine of t over tk. It reminds me of the helix from the last video, but in the k component, instead of t, we have something more interesting, sine of t over t. The parameter interval is all of the numbers between minus 2 pi and 2 pi, leaving out 0. And of course, I really do need to leave out 0 because I probably shouldn't divide by 0. And then I'm asked to find the limit as t approaches 0 of this vector function r of t. Pause the video here and see if you know enough right now to find that limit. So what I'm hoping you did is just simply took the limit as t approaches 0 of each scalar function and wrote that down as a vector. The limit as t approaches 0 of cosine of t is 1. Cosine is a nice continuous function. The limit as t approaches 0 of sine t is 0. And here we have an actual interesting limit to take. This limit of t approaches 0 of sine of t over t. Well, this is a very famous limit from your Calc 1, and that limit is also 1. So this vector function has limit 1, 0, 1 as t approaches 0. If I were to show my work, I would approach it like this. I'm fine with the answer as written on the other board. Take the limit of each individual component function, but I thought I'd write it out like this at least once. This limit is equal to this vector where I'm taking the limit of each scalar function for each component, leaving me with this vector, 1, 0, 1. So limits for vector functions simply take the limit of each scalar function. If we had looked at that same vector function, r of t, but I told you that t just had to be between 0 and 2 pi. Instead of taking a two-sided limit, the best I could do is take a limit from the right. We would approach that exactly the same way. Take the limit from the right of each scalar component function. Limit from the left, same idea. We just do the calculus we know in terms of the limits on each scalar function.